This is a time-lapse presentation of the drawing, modelling and fabrication of the multi-rider, an innovative and adaptable bike-carrying solution for tourers and holiday makers. The project was completed under Southern Cross University's Bachelor of Technology Education Integrated Technology Project in Session 1 of 2016. The project demonstrates my knowledge, skills and understanding within the KLA specialisations of Design and Technology, Industrial Technology and Graphics Multimedia Technology. During the course of a recent in-school volunteering program, I was collaborating with the vendor of the school's 3D printer. My aim was to get the printer running, and the vendor strongly endorsed Autodesk Fusion 360 as a drawing and modelling application. Therefore, I decided this project was an excellent opportunity to learn new skills and apply them to the project. The initial multi-rider design and drawings were completed using SketchUp. Fusion 360 proved to be a more powerful, albeit complex workflow. Viewers can get a taste for the power of this application and hopefully not endure too many of the frustrations I felt in quickly trying to learn the necessary skills to bring the multi-rider to fruition. Fusion employs a 2D sketching interface from which 3D components are prepared. This is similar to SketchUp, although a very significant difference is the use of a parametric approach, which, put simply, allows sketches to later be revised, and these changes are then reflected in the 3D design in real time. The tube hanger was drawn from a 2D sketched plane. The solid section was then extruded to length and the resulting component was then copied to create a second tube. Again, a sketch was used to draw the profile of the upper hanging box. Fusion's excellent tools make short work of offsetting and chamfering components. Cutting solids from sections is quite straightforward with the extrude tool, again using a 2D sketch but on a different plane to locate the cutting points. Aligning the rod locations took me some time due to being unfamiliar with the correct technique. Knowing and recalling the tricks of any software is so important to save time and frustrations. I began to appreciate Fusion's power through the use of joints, which allows components to be attached to each other, either rigidly or through a selection of other sliding, hinged, revolving and ball joints, to name a few. Fusion uses a slightly different and again more complex system of inference points, construction lines and axes. It took me some time to understand this powerful feature set and allow me to easily place objects where they needed to be. Fusion's browser, to the left of the screen, enables management of all the design elements including origins, sketches, bodies and components. Again, developing a clear understanding of this tool set and how to organise it goes a long way to delivering efficiencies for the user. Orientating drawings using Fusion is a dream, although a mouse is a must. The orientation cube in the top right is one of the application's many great assets. At this point, I set up and experimented with a revolute joint, allowing the hanger to rotate downward on the lower bolt's axis. This was then refined to limit travel to 95 degrees. Fusion allows the users to animate their designs. My skill in this area was still in development, as I was later to learn that at least one part of the design had to be grounded, otherwise it'll end up in a strange part of space. Once the upper assembly was complete, I dived into Fusion's new static stress simulation module. This was one of the tools that I was really eager to explore, allowing me to model the performance of my materials, in this case steel, under projected loads. The results include animations of the material stresses and safety factors. Designing the more complex curves of the lower bracket housing are similar to SketchUp. However, mastering some of the arcs required a different approach. Designing in CAD allows great freedom to explore designs, as can be seen from the iterations in this housing. Here, I set up multiple planes offset from the mast. These offsets corresponded to measurements from my vehicle, ensuring fixing points that did not create any conflicts when fitted. Fixing the degrees of rotation on joints allowed me to explore the rack's performance against my design criteria. Animating this proved very useful. Like SketchUp, Fusion outputs drawings to a separate module. It has to be said that Layout, which is SketchUp's drawing application, is very much more powerful than anything Fusion can offer at this stage. Let's hope it catches up in time. My aim here was to print a 1:1 scale drawing which could be used as a template for cutting the 4mm steel plate. Final study simulations using the available materials were performed to ensure final product testing would pass muster. Here we can see the various tools, PPE and raw steel as purchased in preparation for my fabrication. I had two options in the fabricating of the lower plates. I could get them perfectly prepared using laser cutting at a local fabricator for $250 or do them myself by hand. I think the Treasurer said we should live within our means, so I took the later path. Cleaning the steel and simply gluing the templates with paper gave great adhesion. Then, using a grinder fitted with thin stainless steel cutting disc, each section was rough cut, and then each section was trimmed with the same disc, and then, using a grinding head, each section was rough ground. Final clean-up with a bastard, second and final cut files finished the job. This was a really laborious and time-consuming option to have chosen, and I started to think spending the $250 was a bargain. Centre points for holes were printed in the templates. Using a centre punch ensured accuracy for drill positioning. Each hole was 12mm, so a series of pilot drilling was used. Larger internal openings were made by stitch drilling to allow the hacksaw to make those longer cuts. The glue adhered the templates to the steel so well that they had to be removed using a flap disc on the grinder. Accuracy in any project is vital. Here I use a reliable tape measure, my engineer's square and a sharp blade to prepare the drilling points. The magic of time-lapse photography conceals just how time-consuming some parts of this project were. My 115mm grinder was invaluable for the project. According to the Department of Education's 2015 Blue Book, students from Year 9 can use 115mm grinders in the school setting. A grinder is a really powerful and potentially dangerous tool if used improperly. I would strongly stress, the need for considerable care and supervision at all times. Using a lathe, I was able to quickly fabricate 12mm pins for the multi-rider, although I later decided that high tensile threaded bolts would add a higher degree of safety for the use on this rack. This old metal drop saw powered through various cuts reliably, accurately, and always making square cuts. Another invaluable tool was a step drill, which ranged from 10mm to 30mm. Available at less than $20 from Bunnings, it performed very well, quickly, and easily cutting through 3mm steel to a diameter of 28mm. The use of a cutting compound is recommended to reduce heat that can damage the tool. A drill press is an essential piece of workshop equipment. Properly set up and with workpieces appropriately secured, they are powerful, accurate, efficient and generally quite safe to use. Here the multi-rider is roughly assembled and the lower plates are ready cut for welding. I use the grinder to cut fillets in the plates for deeper, stronger welds. My welding skills are quite primitive and a lot of testing, trial and error went into preparation for the final welds, enough to say there is still plenty of room for improvement. Before welding, the pieces were marked out and ground to a bare metal. In the interest of safety, I chose to attempt welds with deeper penetration. This certainly compromised the quality of the weld's final appearance. More training is definitely in order, although I'm confident the welds are really quite strong. Welding uphill is generally regarded to give a stronger result, although it can be a little more difficult to properly execute. Tacking each weld is necessary to eliminate the metal distortion which will otherwise occur during welding. It also ensures accurate placement and easier adjustment of parts before the final weld. Circular welding a round pipe is notoriously difficult, especially without a turntable. Despite lots of practice, I crashed when it mattered and I ended up using a metal filler to hide my sins. Again, grinder to the rescue, this time with a grinding disc to remove the excess weld from the base plate's fillet joints. Product selection is an important part of any successful design. Builder's epoxy putty can be a little bit brittle and prone to shrinkage. This product claims to be ideal for metalwork with embedded glass fibres which interlock to reliably fill voids. Following the drawing phase, I realised the need for a strong eye bolt which could be used with metal cable to secure the bikes to the rack. An additional bolt under the tow receiver allows locking of the rack to the vehicle, giving us extra peace of mind from those bike burglars. Using the grinder, I cut off excessive bolt length and then welded the eyelet onto the mast section. A little cleanup and time to measure bolts using my engineer's square so that I cut them to the desired length. Using the first bolt as a guide, I was able to gang more together for a faster cutting process. When the bolts are cut, the thread is damaged. They can be cleaned up using a correct size threading die, or instead a quick spin on the grinder followed by a little fine filing of the thread pattern. At this point, I'm using the grinder to put a flat spot on the bolt's thread. This allows me to more easily drill through the thread for the fitment of R-clips, which I use for safety in case the bolts undid whilst driving. Nearing the end, I used files, sandpaper and Scotch-Brite to clean up the primer and any burrs, preparing the multi-rider for painting. A quick test to check everything is complete and then it's home for a paint job. The first 2 coats of primer followed by 2 coats of matte black. It would have been far better result to have had the multi-rider powder coated, but the costs were prohibitive. Finishing touches include some 28mm foam tube fastened with cable ties and 45mm self-adhesive foam flats to protect the bikes from knocking on the multi-rider. Plastic end caps were also fitted with a silicone compound to prevent water getting into the various cavities. Finished. Thanks for watching.